you back there? Somebody? Yes, thank you. Where are you? Okay, so I'm Jeff Rao, all of the Terbium magnets. This is work done in collaboration with Michelle Graf. So given this is the highly frustrating magnetism, I probably don't have to find frustration for you. So in this slide, maybe just focus on this corner of it. Namely, what I want to tell you about is frustration through intrinsically anisotropic interactions that aren't tied so closely to the geometrical structure of the lattice. So the sort of paradigmatic example of this is Giddens honeycomb model, which we'll hear a whole lot more about tomorrow. But where it's a honeycomb lattice, where on each bond you have an Ising interaction. The component of the spin, which is coupled, varies from bond to bond. Varies from bond to bond. So this model is exactly solvable and has an exotic gapless C2 spin liquid ground state, but on a more fundamental level, it represents a kind of anisotropic Hamiltonian that is distinct from things like the isotropic Heisenberg model, from the X1 model, from the Ising. So this kind of thing isn't protected by any specific symmetries, but is known to be somewhat closely realized in certain types of heavy transition metal magnets that are built out of edge Shiraki. For example, the sodium pyridates, and more recently, ruthenium chloride. So what I want to tell you about today is other avenues to do this, namely through rare earth magnets. We find very intrinsically anisotropic exchange regimes in rare earth magnets. So these have many of the advantages and many of the properties needed for this that is found in these heavy transition metals. They're very localized, they have large coupling. They have some other issues that you don't find there. For example, the energy scale is very small. So instead of thinking temperatures of 100 Kelvin or 1,000 Kelvin, you're thinking temperatures of 1 Kelvin or 10 Kelvin. And also the exchange is just, in some sense, more complicated. So the sort of conventional dogma would be that you write down what's allowed by symmetry, you sort of throw a dart at that, and then you fit that to, you throw a dart by fitting into a sphere. So usually there's no clear exchange. Even with reams of data, it can be actually difficult to extract these numbers from some kind of data. So what I want to try to tell you today is that there's sort of the simplest context where a lot of these problems are absent, and I think that you can realize intrinsically anisotropic exchange regimes that are highly frustrated, and you can actually have some kind of theoretical handle on to understand where these come from and predict. So what would be my practical, simplest, so I'm going to focus on trivalent terbium. So this is sort of the simplest atomic physics of rare earths, and we'll focus on magnets that are built where the terbium ion sits in octahedra that share edges just like these bad magnets. So this ends up having similar exchange physics. It also affords us a well-characterized test case to make sure that everything I'm saying theoretically actually has some bearing on real world. Okay, and so just to make the point that these edge-shared lattices of octahedra are fairly common and relevant for materials we care about, here's a sampling of different lattices you can build out of this. You have triangular lattices that have been found in things like the spin liquid candidate terbium, magnesium, gallium oxide. You have a honeycomb lattice that we saw before. Then you have pyrochlore lattices like this, both of edge-shared octahedra that are found in spinels. There's many more. There's a whole book about what kind of lattices you can build out of perfect edge-shared octahedra. These domain, hyper-honeycomb, hyper-domain, harmonic honeycomb, things that don't even have good names. Okay, so we want to talk about the exchange physics in terbium magnets. We have to talk about the single ion physics. So this is relatively simple. As I said, you just have a single hole in an otherwise filled F shell, so 4F13. So this is why the atomic physics is simple. You basically just have the L 3s equal half states. Spin orbit splits this into a 5-half and a 7-half. Then this lower 7-half state is then split again by crystal field. So for all the compounds I'm going to tell you about, it's all some kind of trigonal crystal field, so it's not perfectly octahedral. You might have some squeezing along some sort of body center type directions. And so these are just simple single electronic states that can be built out of combinations of these J7 half states. So this gamma 4 doublet, which typically comes out when you have a near octahedral environment, generically takes this form. It's some arbitrary combination of JZ7 half, JZ1 half, JZ5. What is exchange? So exchange inheritance is a little more complicated than in transition metals because of the large number of states that are present in the single line of physics. So this is sort of the worst case I've shown you here, using the free ion spectra of trivalent rare earths. Each one of these is manageable. Right? So if you're going to consider the exchange on something like terbium, which is somewhere in the middle of the spectrum, then you're going to have charge transfer processes that take you to neighboring valence states. And this can involve virtual processes through this whole tower of states. So for terbium, it's particularly bad because you have a few thousand states, and thus the actual details of the exchange can get quite complicated. Terbium is a little better because it sits near the end of the periodic table, but even there, you're talking about on the order of 100 states in these virtual processes. So it looks something like this. If you have a one-hole enclosed shell, one possible state is if you close the shell, and that's just a nice simple state. The other possibility is to make a pair of holes, then you get 91 possible states that span about 10 UV. So what I'm going to describe to you is sort of the simplest way to try to compute these exchange interactions, which is you include these charge transfer processes, and then you assume that in the middle here, the virtual states that are involved are just free ion states. So this is a reasonably good approximation of errors, and then once that's done, we project into these gamma 4 doublets, which are the crystal field ground states. So a little more practically, what you need is some kind of estimate of overlap integrals. That is the 4F ion overlap with its neighboring ligands, has an overlap with the neighboring 4F ion, has an overlap with the regular ground. You carry out the general perturbation theory using the full free ion atomic states for the 4F12, 4F14 states, and you take that and project it into this low line level. So what you need basically is the geometry of the bond. So you need the crystal structure. You need to know what you're projecting into, what this crystal field ground state is. So this again is material dependent. And then you need to know a bunch of these sort of theoretical factors. What are these overlaps? What are these exact free ion parameters? So what comes out? This model that looks like this. So for all the cases of interest, the bond symmetries are essentially the same. And you get a model of 4 symmetry lap exchange interactions, something that's Ising-like, something that's sort of XY-like, and then these two bond-dependent terms. And this is, you write this down in exactly the same way for the pyrochlore lattice, for the triangular lattice, for the honeycomb lattice, as long as you color these bonds.
Excuse me, what is this S?
S is the pseudo-spin of this lowest ground level. So you take the full angular momentum and you project it. The full exchange Hamiltonian you project it into these states. Okay, so you can make this a little more familiar. These JZZ and J plus minus are familiar and comfortable for a lot of people, but it'll turn out to be more useful to recast them in these sort of a more global frame, where instead of tying them to the local crystal field axis, we tie them to some overall coordinate system. So for the triangular and the honeycomb cases, this gives a sort of familiar model, this JK gamma gamma prime model, which is known in physics as the cadet model. In the pyrochlore lattice, this is something we've seen a little bit already, this J1, J2, J3, J4 model. All I've done here is sort of relabeled it. We have an isotropic Heisenberg exchange. We have a Kedem type exchange that's bond and Ising. We have this symmetric off-diagonal exchange. We also have Giselle-Shinsky-Moore interaction. Okay, so that's sort of a sketch of how you do the calculation. You do the calculation, you get numbers for these quantities. So you get a JK of gamma, a gamma prime, a JK of D, a gamma. So do we expect this to work? Should we trust it? So another nice thing about this is we have a sort of ready-made test case. So this is a breeding pyrophore compound, barium, terbium, zinc oxide, which has this attractive feature that in some sense it is very simple in that you have a very similar pyrophore structure as you find in these spinels, except these individual tetrahedra are pulled far apart. The distance from here to here is twice the distance from here to here. So to a very good approximation, the exchange on this bond is negligible, and you get essentially decoupled tetrahedra. And because of that, the model is theoretically controlled, and then through detailed analysis of the experiments, you can extract very precise numbers for these exchanges. So what you get is highly structured, not generic, not throwing a dart at the board, something that looks very specific. Basically, you get a positive J, antiferromagnetic coupling. You get small symmetric anisotropy, small Ka, small gamma coupling, and then a large indirect VM. And this matches very well with what you find from fitting to this pair. So it seems in this case where you have very nice edge-shared octahedra, not too strong of trickle distortion, this can give you a almost quantitative estimate of the exchange. So more broadly, you can look at how this depends on things like crystal field parameters. So what I'm showing here is some parameterization of this ground doublet, which again varies from material to material. So perfect octahedron, say here, and then this would be a perfect cube, and then in here is some kind of trickle distortion. So what I've drawn here is basically what the dominant exchange is. So if you see gray, what it means is that nothing's dominant. And then when you see a bright color, it means one of the exchanges is dominant. So this red area here is saying that the Heisenberg antiferromagnetic coupling is significantly bigger than all the rest. So this island of dominant antiferromagnetic coupling is where this reading power sits and gives you this extra structure. But there are also other sort of islands you can see here of, for example, dominant DM of ferromagnet. If you there's a duality transformation that you can do that where you can see there's something that's equivalent to a Kadab model, something that's equivalent to this pure gamma model. So it seems like there's some non-generic regime in this exchange thesis. As you move away from that, you can understand why the next term is DM. Basically, you start with pure octahedral cage, and basically it kills everything but the J term. You move away from that, the first thing that picks up is DM. As you break the inversion symmetry, as you add the triple distortion. Okay, so this is sort of a general picture, sort of validated on this breathing power core. What implications does this have from other materials? So the closest relative are the rarest analysis. So we have a chemical formula of this form, where this power core lattice and edge-shared octahedra, relatively undistorted. They're highly frustrated. The nail temperature seems to be quite a bit smaller than the exchange scale, but eventually they do order. We have this nice transition here in all four of these compounds. And the ordered state appears to have sort of gapless and nearly dispersed excavations, similar to what has been discussed in erbium titanate. You can see that here from almost a T-cube law in specific heat at very low temperature. So if you estimate the crystal field parameters from a neighboring material, it's hard to extract into the turbine. If you rescale the ones appropriate for erbium, you can sort of put it on this exchange diagram and ask what the numbers are, and you get something very similar to this breathing power. You get small symmetric anisotropies, large indirect DM. So this, classically, with these two small numbers, gives you this gamma 5 state that we heard about for erbium titanate, and this has actually been directly measured in recent neutron scattering. Okay, so this sort of nails it down somewhere in the phase diagram. But we can ask, what is the physics of this state? So one possibility is that it's similar to what we've heard in the previous two talks for erbium titanate. Basically, it's sort of semi-classically relatively robust. You get well-defined Magnon modes for some order by disorder selection effect that picks up the state. If you compute that, you would get psi 3 from one order by disorder, and then you'd expect something like a pseudo-Goldstone mode of about a tenth of an MeV. A pseudo-Goldstone gap of about a tenth of an MeV. And this should be visible in things like an elastic neutron, low temperature specific heat. There's lots of ways to measure that. So a more interesting possibility is that instead of being similar to erbium titanate, it's actually closer to the ytterbium titanate. So unlike erbium, which sits in the middle of this gamma 5 phase, these parameters, this large J, this indirect EM, actually put it near the boundary of the gamma 5 phase and the ferromagnetic. And so with an appropriate redefinition of parameters for ytterbium titanate, this is a very similar qualitative regime. Basically, if you take a Heisenberg antiferromagnet on the power core lattice, add indirect EM, you sit on a phase boundary between the splayed ferromagnet and the gamma 5 phase, and then the which phase you land in is tuned by the sum of these two symmetric ends. So the idea would be ytterbium titanate, ytterbium stannate might sit up here, ytterbium germanate might sit down here, the spinels might sit down. So there's sort of other indirect evidence for this. one of the characteristics that you see in these ytterbium compounds is above the ordering temperature, there's some sort of broad peak in the specific heat, which is supposed to be onset as a kind of correlated paramagnet. This is also seen in these phenels. You can see it here. Also, the ordered moment is strongly reduced, indicating strong frustration. So the question, the interesting question is then, does it have the same dynamics? So one of the hallmarks of these ytterbium compounds is that even though they have ordered states, gamma 5 displays paramagnet, the dynamics of the state are highly unusual. Instead of the expected gap magnon mode you might get in a simple anisotropic paramagnet, you get some broad continuum of excitations. And this is similar to what you see in the germanium, which has the same gamma 5 ground state you expect in these spinels. So this could be a new realization of this kind of physics in an entirely new class of compounds. And so it could resolve certain questions about whether it's intrinsic or extrinsic to these materials due to disorder or strain, these kinds of things. There's a whole new material platform to explore. Okay, so since I only have a certain amount of time here, let me just sketch one application to another type of compound, a non-powerful compound. So what happens if you come back to this original thing that I said about honeycomb magnets? If I say, these can realize gas model, what if I stick this scenario I said with ytterbium on one of these labs? And so it turns out the physics is significantly less interesting in some sense. Because the ytterbium in an occasional cage sits here, near this gamma 6 doublet, rather than here, near this gamma 7 doublet, which is the same J effective half doublet that's acted in the CADEV compounds. You basically get something similar to what you find in these power cores. Large anti-ferromagnetic coupling is your dominant interaction. But because these have inversion symmetry, there's no generation of DM. You can only generate symmetric anisotropies. And those are generated much more slowly. So you get this sort of wide window of basically an almost perfect Heisenberg anti-ferromagnet, even though this compound, this large orbital coupling, etc. Now, if you really stretch this, you say, well, maybe I changed the bond net, or maybe I distort the crystal field parameters, you can generate genes where you have actually a dominant CADEV coupling. The CADEV coupling is an order of magnitude or 2 higher than any of the others. It's unclear how realistic this is, but given that there's been very little studies on these, it's still in the realm of possibility. Okay, so let me sort of wrap it up there. So what I've tried to sketch you here is there's a sort of corner of the physics of rare exchange where we can have some relatively reasonable idea of what's going on. This gives, is invalidated for this breathing power core compound and has further sort of predictions for these spinels, which, unlike, which are consistent with the experiments today. There are also other applications to this triangular compound, which I didn't want to get into since there's a disorder is, there's a structural disorder, which makes it somewhat more complicated. There's also a little bit of something I've glossed over here, which is when you go near this other limit, far away from this perfect octahedron, the exchange physics becomes quite sensitive to the details of the calculation, the exact numbers you put in, the exact overlaps you put in. And this is somewhat similar to the cancellation that happens in these transition metal CADEV compounds. It makes it quite difficult to make any clear statements. But it could also be why these power core materials, which sit closer to that limit, are much more rich in terms of their exchange. And if you want details, it's all there. All right, thank you.
Thank you very much, gentlemen. Talk is open.
I just would like to make a message. Oh, I would just like to make a comment that there are chain-like ytterbium particles where the spin dynamics is very well described by Spielberg and Heisenberg. Newtonian and the spectrum is incoherent continuum. So it fits very nicely to
Comments or questions? So if you ignore the cationic disorder for the ytterbium triangle lattice material that you mentioned,
Yeah.
What kind of change can you make it?
Okay, so it's somewhat anisotropic, but it's not so anisotropic. You have to be a little careful because to do these calculations, one does require a relatively good estimate of the G factors, and that's hard to get out of experiments on turbine compounds. But if you just take some nominal values, you don't get something so close to what's been fit, assuming that the disorder is not there. But the calculations do.
So it's not.
Yeah, I got some. They vary strongly on exactly what bond angle you put in and exactly what crystal field parameters you put in. More on the bond angle than on the crystal field parameters, but it makes the thing kind of ambiguous. So physically, that might mean that it means that the exchange disorder is strong. You'd expect it to be strong based on these calculations, but it makes it hard to say what the ball guessing is.
Okay. More questions? Comments? Yeah. So.
Yeah, so as you know very well, with the monochromatic, if you have only indirect folding, you can just verify without exchange, hydrogen exchange.
Yeah.
Right? So is that true in this case that you are talking about with orbitals, many of them?
There is, strictly speaking, no. So
So you always have hydrogen.
there's always something else.
Why is that?
Okay, so this is a bit technical, but so in the KDF case, right, you have these pi overlaps. If you just have the pure oxygen channel. And so for the F case, you have more than just the pi overlap. There's also the sigma overlap that's there even in the ideal geometry. So it's just a difference for F orbitals.
I see. F and P is different from E and P.
Yeah.
Okay.
Jeff, I expected from this first principle type of approach to have some probability maps where the such and such material would land in terms of parameters. Do you have kind of to speed the available parameter range?
No. So what would be useful, I think, to get out of first principles in this case would be things like the overlaps.
No, I called your approach as the first principles approach. So I expected from it to come some kind of color map where you would say that this is the region where parameters are most likely to land.
Yeah, so again, this is material dependent because it depends on the crystal field and exactly what that implies about the doublet. But one might say, for example, the spinels, I wouldn't expect it to be too far from here. Making that quantitative is difficult because the crystal field, for example, doing a simple point charge calculation is not quantitative for these systems. So you have to fit it from experiment, and for terbium, it's not clear there's enough data in the levels to do that. So.
So your calculations are, they give you the attractions or estimate the attractions at a near neighbor level.
Yeah.
Is it a bridge too far to estimate next near neighbors or such?
One could do it in just the sense that you could write down the calculation. I don't think I would trust it, in the sense that this already has a handful of free parameters which are difficult to set, certain atomic overlaps, certain atomic energies that we're sort of estimating, and then we're checking that things aren't too sensitive to them. And so for these spinels and such, they aren't. But if you start adding, for example,
Well, I was just wondering if you could estimate what, what fraction of what's a typical scale for the next neighbors?
yeah, no. So actually here, we don't get the scale, in some sense. Without sort of an ab initio estimate of what these overlaps are, we don't even get the scale. So you just get ratios.
Okay. More questions, comments, thoughts? Yes, please.
You saw the three factors of parameter. Charge potential. So can you express some suggestion about Ligan Hall effect or
Like what, sir?
Ligan Hall or such fluctuation? Your theory is strictly only insulator.
This is for the insulator, yeah. So this is a caricature. Right, so in reality, it goes from the rare earth to the ligand to the rare earth. And there's some cyclic processes in there as well. But,
Okay, so your theory is to the realized 3 class state.
yes,
Okay, thank you.
yes.
Well, questions? Seems not to be the case, so we thank the speaker once more for his presentation.